Hey, folks. Thanks for doing what I expect as far as listening and watching the video. I think you're doing what you can to understand this concept. Make sure you're asking me questions if I'm not making this clear. Okay. So, our notes are going to look like this today. I can graph a system of inequalities and find the feasible region. That's what we're trying to do. So, what does the feasible region look like? The feasible region is this area right down here. Okay. And I'm going to walk through all of this stuff, but feasible region is when both inequalities are being made true. So, all the points that make both inequalities true. And you could write that right over here. It's all the points, all the values or points, all the points that make both inequalities true. All the points that make both inequalities true. And so I'm going to walk you through how to do that in the next little graph here, in the next little slide. But first, I just thought we'd take a look at some pictures. So all the points that make both inequalities true. That's what is really important today. We have more than one inequality, so both of them have to be true, and that's called the feasible region. Now, that region could be bounded, meaning like it could have complete containment. It doesn't go on forever. So here's a bounded feasible region. And then it could be unbounded. This one's unbounded because the points would keep going in that direction. All right, so that's what those two words mean. I would add that to your notes, like, put the word unbounded here and put the word bounded right, like, I don't know, in here somewhere, bounded, and then draw like a little arrow there. So I think it's going to take, at least 3 inequalities to make something bounded. If you only had 2 inequalities, it seems like it would go on forever. And math, it's tough to make those always type conclusions, but it feels that way to me, doesn't it, to you? That you would need to have at least 3 inequalities to have 3 sides to contain it. So we'll investigate that a little bit more too. But first, let's figure out, how do you do this? How do you solve this system of inequalities? Okay, so I've got a little graph all set up here for you, and we know what the answer is. We just saw it on the other slide. So if I mess this up, you'll know I messed it up. So first thing you do is you treat it like an equality. Okay, so y equals 4x minus 3. I need to graph the boundary. So that's what I'm going to do right now. I'm going to graph the boundary, and I'm going to make it a solid line. I was trying to do 2 things one at the same time. So I'm going to make it solid. Why am I going to make it a solid line? Well, because it's an equal to right there. That makes it a solid line that I'm going to make. Now, I'm pretty good at graphing equations that are in slope-intercept form. It tells me the intercept is -3. Right there, that's my y-intercept. Y-intercept equals -3. And then my slope is 4. So I'm going to go up 4. 1, 2, 3, 4. And then I'm going to go over 1 to find another point. Now, I'd like that line to be perfectly straight. I'm not going to pull out a ruler or anything like that. I'm just going to do my best. Okay, now it would help if I did another one. 1, 2, 3, 4, 1. Okay, so I'm just going to put another point as a target on there. All right, so here's my boundary. 1, 2, 3, 4, 1, right? I can go down. I can make both of them negative, down and left, and then I would have a positive slope, right? +4 slope. So I made it solid again because it was a less than or equal to. Now I need to test and shade. Which way am I going to shade this thing? And the way that I test out a point is I love having the origin to one side of the line. So if this point, the origin, 0, 0, if 0, 0 works on my inequality, then I'm going to shade in that direction. If 0, 0 doesn't work on my inequality, then I'm going to shade the other way. So here comes like part 2. I need to test a point. Test a point. And the point I'm going to try every time is the origin, because it's about the easiest arithmetic that you can use. So, oh shoot, I don't want equals there. I want a less than or equal to 4x minus 3. Okay, that's what I'm testing it in. I take 0, I put it in for y. I take 0 and I put it in for x. And I see 0 less than or equal to -3. No, it's not. 0 is greater than -3. Like if you had the number line, here's 0, here's -3. Any point to the right of another point is bigger. So 0 is bigger than -3. And so that's false right here. It's not less than -3. So I do not want to shade in that direction. So I'm going to shade in the like in this direction over here. So I want to shade this. This is my feasible region so far for that one line. Now, I need to have more than one line really technically to have a system of equations and to have truly probably a feasible region. So let's do the other line right now. Switch back to my pen tool here. And here we go. So the other line is, shoot. Let me see if I can fix this here. Okay. And okay, so my line number 2 is -2y, -2y greater than x. Okay, but wait. I'm going to treat it like an equation, right? So I want that not to be an inequality right there. I want it to be an equal sign. And this one, let's see, what could I do to this? I mean, it's not in slope-intercept form, but it's almost there. Like I could divide both sides by -2, right? Divide both sides by -2, and I get y equals -1/2 x. There's lots of ways to do this, to graph lines, but I think that's probably good enough. I divide both sides by -2. Now I can see there's my slope, right? I want that to be my slope. And then my y-intercept over here, let's see, I got like +0, right? So I have no y-intercept, or y-intercept is 0, I should say. I have a y-intercept, but it's equal to 0. So y-intercept equals 0, 0, 0. So no, oh shoot, man, I got to use the origin for one of my points. So that means I can't use the origin to test to see if it's true or not. I'm going to use a point to the left or the right of the line. Okay, so here we go. So slope of -1/2. How do I do that? I could go up by 1, and I could go back 2. Right? And I could go up by 1, back by 2. So let me make a little like triangle here. I went up 1, and then I went back 2. So either the numerator is positive or the denominator's, either the numerator is positive and the denominator is negative, or vice versa. The numerator is negative and the denominator is positive. So let's do one of those. I go down 1 and I go over 2. Oh, I already knew that point. Down 1, over 2. And then I'm going to connect those points together, right? Ooh, dash line. This one, because it's just a greater than sign dashed, right? So we talked about this before. So hopefully this all seems familiar. Like, why is he going so slow through this? Hopefully you feel that way. If you don't feel that way, I'm glad I'm reviewing this for you. So dash line, right? Now we got to decide which way we're going to shade. So I test out a point. So let's go over here to my highlighter. I'm going to change colors. And let's see. I'm going to test out the point. Shoot, I don't want to be in my highlighter yet. Let's try, how about we try, oh boy. I'm going to try this one right here. It doesn't matter. You just want a point that's either above the line or below the line. Okay, so I'm going to test out 0, 1 because it has a 0 in it. So I'm going to put, let's see, a 1 in for y. And then I got to change back to my inequality. Where the heck is, okay, shoot, it's the inequality, -2y greater than x. Testing. I'm testing out 0, 1. Here we go. So I put a 1 in for the y. So -2 times 1. Is that greater than 0? Is -2 greater than 0? No, it's not. That's false. Okay, so I do not want to shade toward that point. Oh, shoot, that point right there. That was my testing point right there. So I'm going to shade the other way, away from it. And so here we go. I'm going to shade down in this direction. Okay. And I'm not sure if this is going to show up as green down here like it did in their example. No, it goes right over the top of the yellow. But where we got yellow and blue, this is my feasible region, right? So let's label that guy very clearly as our feasible region right down here. Feasible region. Okay. So is it bounded? No, it's not bounded because it would go on in that direction forever. I know you might say, well, yeah, it has some bounds. It has this line over here and it has that line over there, but it's going on forever. So we called it unbounded. All right. I hope I'm making this clear. If you feel like you're ready to just knock out the homework, don't watch video 2. I'm going to do example 2 if you need some more help with that bounded situation, that other drawing that I had in here, right? Hey, thanks for watching.